Baker. I'm representing the gold team. I'm going to discuss the filter wash station. Just a brief outline of what I'm going to go over today. I'm going to go over the background of our system briefly, the theory behind our system, the theory behind the modeling we did on our system. I'm going to briefly go over the results for the SSOC, the step response modeling. Then we'll go a little more in depth on the frequency response modeling, the root locus, and the proportional only controller modeling. A little bit of background on our system. It is at the publicly owned Treatment Works sewage treatment plant. It is 3 filter presses that filter out the sludge in the wastewater. The plates must be cleaned, and the range that they need for the pressure to clean the plates is between 8 and 20 pounds. This is a diagram of our system. You have your filter pump, and then you have it goes to the filter washing nozzles. You have 2 valves over here on the side. For our experiment, both of these valves are open. You have your frequency your transmitter, the flow transmitter, then you have your flow controller, and then you have your actuator that actuates the pump. The input of our system is the motor percent power, and the output of our system was the flow rate in pounds per minute. Brief theory on the background of our modeling of our system was the frequency response. You use the input baseline and amplitude to get a gain, a dead time, and a time constant. For the proportional only controller modeling, we had an input baseline, proportional gain, the input set point, and the change of set point, and you would get a decay ratio, settling time, offset, and overshoot percent. This is our results for the steady state operating curve. And this is our FOPDT model against our experimental data for the step up. And this is for the step down. This is our frequency response. What we did was we took 3 values of the T to use the student T statistic and use the equations to find our amplitude ratio and our phase shift. When we got all the data from our experimental data, we created the Bode plots, and from our Bode plots we acquired the K value, the order, the frequency, the ultimate frequency, the KCU, the time delay, and the tau. These are the equations used for modeling the frequency response. After we did our experimental frequency data, we created a model and then plotted our experimental data against our model. And we adjusted the model to best fit our experimental data. And the gain we acquired from that was 1.6 pounds per minute per percent, a dead time of 0.7 seconds, and a time constant of 0.7. This is our root locus for the system. We use the root locus to find the different KC values for critical damping, the 1/500th decay, the 1/10th decay, quarter decay, and ultimate KC value. For the quarter decay, or for the critical damping, we had a KC value of 0.2 pounds per minute. For the 1/500th decay, we had a 0.44 pounds per minute. For the 1/10th decay, we had 0.99. For the quarter decay, we had 1.3. And for the ultimate, we had 2.1. For the proportional only controller modeling, these are the equations that we used to create the model. Your M of T was the controller output, your M bar is the controller bias, and your KC was the controller gain input into the system, and your ET was their error. This is a sample of one of our proportional only controller models. This one was at KC equals 1.3. From that, we acquired the decay ratio by taking the value of the first peak from the steady state and the value of the second peak to the steady state, and it was the ratio between the two. Then we determined whether it was monotonic or oscillatory. This one was oscillatory. The settling time was taken from the time that the system had its input all the way to where it reached steady state again. And the settling time was 5.5 seconds, and the offset between the two from here to here was 0.8, and overshoot we had was 9%. This is the data from all of our proportional only controllers modeling. We did a quarter decay, 1/10 decay, 1/500th critical damping, ultimate, and then we also did an overdamp case and 4 other underdamp cases to get a little bit more data. I rearranged the data a little bit from what we had it in, so you could see in order from KCU, from the smallest KCU to the largest KCU, and we found a few trends in the data from the KCUs. The KCU versus the decay ratio, as the KCU went up, the decay ratio also increased. And as the KC went up, the offset decreased. So the higher KC value you have, the smaller amount of offset you have. The overshoot percent versus the KC went up, and the purpose of this was to determine that if your KC, as your KC goes up, by choosing your KC value, you can either choose to have a smaller amount of offset and a larger overshoot, or a smaller overshoot and a smaller offset. In conclusion, from our root locus, we had a critical damping KC of 0.2, a 1/500th decay of 0.44, a 1/10th decay of 0.99, a quarter decay of 1.3, and an ultimate KC of 2.1. And then when we plug those into the model along with some extra data points, we had decay ratio for the 0.2 was not applicable, and it was monotonic, and it had a settling time of 2 seconds, an offset of 2.8, and an overshoot of 0. For KC equals 0.3, the decay ratio was not applicable. It was monotonic, had a settling time of 1.8, an offset of 2.3 seconds, and an overshoot of 0. For decay ratio, for KC equals 0.8, the decay ratio was not applicable. It was monotonic, and settling time was 1.1 seconds with an offset of 1.2 and no overshoot again. And when we did the KC equals 0.9, the decay ratio was 0.07. It was just then starting to be oscillatory. The settling time was 4.5 seconds. The offset was 1.1, and the overshoot percent was 3.3. For KC equals 1.2, we had a decay ratio of 0.2. It was oscillatory with a settling time of 5.2, an offset of 0.9, and an overshoot of 5.8. For KC equals 1.3, our decay ratio was 0.22. It was oscillatory, settling time of 5.2, an offset of 0.9, and an overshoot of 5.8. For KC equals 1.3, decay ratio was for 1.8, decay ratio was 0.76. It was oscillatory with a much larger settling time of 11 seconds, an offset of 0.6, and an overshoot of 15%. And then KC equals 2, we found to be our KC ultimate when we did the modeling. Our decay ratio was 1. It was oscillatory. The settling time, it never settled because it was at KC ultimate. The offset was not applicable because we couldn't find a steady value, and the overshoot was 100%. The KC 2.5 was our overdamped case, and because it was overdamped, we could not find a decay ratio for it. It was oscillatory. It never settled because it was overdamped, and the offset was not applicable, nor was the overshoot percent. Are there any questions?